Hello, welcome back. After introduction with the first order and second order PDEs, classification etc. So, now let us proceed for the numerical discretizations and the various techniques to compute partial differential equations. Okay. So, if you recall the classification, we with respect to second order in general we classify as parabolic, hyperbolic and elliptic. So, though it is I mean nice to start with the first order and then second order, but in general in particular when you deal with partial differential equations numerically, normally we start with the second order. So, let us start with second order and then see how we proceed further. Okay. So, the title I gave is finite difference approximations. Okay. So, two parabolic, because I would like to start with parabolic, but before we start with parabolic, so what is the general assumption? So, the general assumption is, so the functions and derivatives are single valued, okay, single valued, finite and continuous of the independent variables, say x, y, z, t, etc. Okay. So, why this assumption is required? So, this is a concern. So, this assumption is required because as you can see when we deal with the partial differential equations. So, you get derivatives with respect to all the independent variables. Okay. So, now when we approximate these derivatives, we need to expand them in Taylor series. So, we need these assumptions. Okay. So, let us start how we approximate. So, consider say u of x plus h. So, x is the independent variable and u is dependent variable. Okay. So, this we go for Taylor series expansion and h is increment. So, h u dash of x plus u double dash of x plus u 3 of x plus. So, I am not writing the remainder term because in first order when we are doing ODEs we have discussed thoroughly the Taylor series method. So, therefore, I just write a remainder term. Okay. So, let us call this 1. Okay. So, then similarly let us consider x minus h and expand in Taylor series. So, this will be okay. So, alternate signs. Okay. So, plus the remainder. Okay. So, now we had 1 u plus this term. Okay. So, this expression, then 2 is alternate signs. So, say we add 1 and 2. So, this implies left hand side Okay. Then right hand side. So, since it is alternate signs, so u will be so we can see u and this u 2 times and these 2 terms get cancelled. So, it is like that. So, the first term will be and h coefficient is 0 since h square by 2. So, this will be this. Okay. So, third will be cancelled. So, then I am putting order h 4. So, which means the first non-zero term which we are throwing it is starting from h 4. Okay. So, now from here we can obtain approximation for okay. So, this u double of x is approximately by okay, by so this coefficient is h square and this term this is a plus sign here and this goes to the left hand side. Okay. So, then since I have divided by h square, so now this becomes okay. So, this is typical approximation. So, generally we write it as okay. So, this is an approximation for the second order derivative. Okay. So, remember we have added it. So, now let us see what would happen if we subtract 1 subtract 2 from 1. Okay. So, then you can see so, if you so the first term is u. So, that get cancelled and we get 2 times h and second derivative get cancelled. Okay. So, we get h cube by 3 okay. So, again from here we get approximation for the first derivative. So, since we divide by h, this is okay. So, in by adding we approximated second derivative okay, and by subtracting we approximated the first derivative. Okay. So, what is happening? So, geometrically what is happening? Geometrically star approximates the slope of the tangent. Okay. So, in what sense? So, let us see. So, geometrically okay, suppose the function like this and say this is x minus h and this is x okay, and this is x plus h. Okay. Say this is point P, say this is A and this is Q, okay. And the chord this is P Q. Okay. So, the function value here u of x minus h and the function value here. Okay. So, this is u of x and the function value here u of x plus h. Okay. So, geometrically what is happening? So, the formula which we have obtained u dash of x u of x plus h x minus h by 2 h. So, this approximates the slope of the tangent at A, because it is x. So, what is x? X is the point A. So, therefore, approximate the slope of the tangent at A by slope of the chord P Q. Okay. So, slope of the tangent, okay, at A has been approximated by the chord slope of the chord P Q. Okay. So, this typically is known as central difference approximation. This is because you are approximating slope here by the slope of the chord. Okay. So, so you are using a past point here and a previous point here. So, the difference is so this is for equidistant. Okay. So, the same star can be generalized. Okay. So, the star can be generalized. So, say, so this is x some x I minus h, then this is x I. So, this is x I plus h. So, this is for equal spacing. Suppose we denote it by x I plus 1 and this need not be equal spacing. Okay. Unequal spacing. So, this approximation can be generalized. Okay. U at x I is okay. So, this is so delta x I increment square. Okay. So, this is a generalization. Okay. So, now let us see how the general approximations are done for first derivatives etcetera. Okay. So, again let me consider this. So, this is so generally we consider equispacing for the simplicity. However, for more complex problems one has to go with unequal spacing. Okay. So, now this is x, this is u. Okay. So, now one can approximate the slope, slope of the tangent at, so P A Q let us call at A by slope of the chord earlier P Q. So, instead of that A Q. So, this is u of x plus h, u of x and u of, sorry, this is x minus h, x plus h. So, this is okay. So, if we do this, then the corresponding approximation which we are going to get is, what will be the distance, this here to here, it is just h. So, x plus h by h. Okay. So, this is called forward approximation. Okay. Similarly, if you approximate, so dot 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 by chord P A, then we have u so this is backward. Okay. So, this is the general technique of approximation. Okay. So, having done the approximation, okay. So, let us see consider maybe a first order PDE where you have a simple situation, two independent variables and one dependent variable, and see how the corresponding discretization leads to the corresponding difference equation. Okay. So, let us start with a simple example. Okay. So, we are considering a first order PDE, say so x and t are the independent variables, u is the dependent variable, a is some constant, okay. And when we define a PDE, it would be better to completely define it by prescribing the corresponding boundary conditions if it is only space dependent, boundary and initial conditions if it is both space and time dependent. So, since in this present case it is dependent on both space and time, so it would be better to completely define the problem. So, with respect to space it is one derivative. So, we need initial condition say u 0 of x. So, this is our initial condition. Okay. So, this is nothing but at t equal to t naught. So, generally this is taken as 0, okay, because you can see here. So, then it is one dimensional with respect to space and the derivative is also only first order involved. So, here with respect to time first order involved. So, we need to supply only one boundary condition, say u of t. So, this is boundary condition. So, this is at x equals to some x naught, in this case taken as 0. Okay. So, now the problem is defined. So, let us say we would like to start discretizing say 2, say 2.1. Okay. So, 2.1 and give 2.2, 2.3. Okay. So, now if we discretize 2.1, okay. So, first we have to discretize this. So, that means first order with respect to time we would like to discretize. So, since this is a PDE which involves two dependent variables. So, we have to define how x is being discretized. So, x is being discretized as x I plus 1 equals to x I plus h equispaced. So, I equals to 0, 1, etcetera. So, then t j plus 1, t j plus k. Okay. So, we discretize, this is the notation. Accordingly, u of x t at a particular point x I t j, we are going to denote it by u of x I t j, this is u I j. Okay. So, this is our standard notation. Okay. So, now with this notation let us approximate the first derivative as follows. So, dou by dou t of u of x t. Okay. Of course, at a point x I t j. So, this will be forward time by delta t. Okay. So, this is forward time, then minus by 2 delta x. So, this is central space. Okay. So, I have used earlier as h and delta t as k. Okay. So, now if you substitute this in so we get, okay. So, what is, you can see this is with time plus constant times with space. So, what you get u I plus 1 j minus u I minus 1 j by 2 delta x, this is a times plus u I j plus 1 u I j by delta t. So, I just swap the terms. So, I put this first and then this. Okay. So, this is the corresponding discretized version. So, this further can be simplified u I j plus 1 j plus a delta t by delta x by 2 u I plus 1 j minus u I minus 1 j, okay, So, this equals 0. So, this is the corresponding discretized equation. However, if you recall the original equation, we have initial condition and boundary condition. Okay. So, it is our duty to discretize these as well. Okay. So, let us consider the initial condition. So, initial condition u of x 0 is u 0 of x. So, this correspondingly it will be discretized as u of x I 0 u 0 of x I. Okay. So, further in our notation u I, and this is for all t j, okay, t j equal to 0, right, for all j t j is 0. So, this is the usual notation. Okay. So, u 0 of x I. So, we should not get confused with this notation. So, I retain this. Okay. So, for example, if we say this is just a function of x, then this would be f I. Okay. So, this is for all I which depends on the increment. Okay. Similarly, boundary condition. Okay. So, the boundary condition we have u 1 of t. So, say some g of t. So, this is 0 t j equals to z of t j. Okay. So, this will be the corresponding discretization of initial and. Okay. So, now if you look at carefully, given the initial and boundary conditions, okay, given the initial and boundary conditions, we have to solve. So, it depends on the boundary and depending on at which time step. Okay. So, let us go to higher dimensions, okay, not higher dimensions, the higher order derivatives. Okay. So, because as I mentioned, this is just to give you an idea. Okay. First order we have taken and then we have shown the discretization. But now, let us proceed to the first class of the second order PDE, which is the parabolic case. Okay. So, let us start with the parabolic case. Okay. So, this involves several variables. So, therefore, functions of several variables. So, before we proceed to parabolic, so here assume u is u of x t, okay, two variable which I have already shown. So, now we can have a little better picture. Okay. So, you can see, so this is x and this is t. Okay. So, do not get confused, earlier I have plotted a graph x with u, but here we are trying only the discretization of the domain. What is our domain? Depends on the x range and depends on t range. So, this is our domain. So, now So, this is the discretization of the domain. Okay. It goes like this. So, you can see so this is a H which is our delta x. Okay. So, then this one is k which is our delta t. Okay. So, if you take any point, so this p point, so this is at some x I t j. Okay. So, now depending on the boundary, this depending on the step size, the I will be decided. So, let us say this is x naught, typically 0. So, if you start x naught is 0, so then depending on the step size, x 1 is h, okay, so on, right. So, let us go for the second order discretization. So, I have already shown in the beginning, we would like to approximate at, okay. So, this is given u of I plus 1 j So, this I have shown in the beginning. How do we get it? To consider the u of x plus h. Okay. So, then consider u of x minus h expansions, then add them, we get this. Okay. So, this is, remember, this is the derivative with respect to x. Suppose the derivative is with respect to t. So, this is approximate. So, this will be u I j plus 1 by k square plus order of k square. Okay. So, this is typical second order approximation. Why we are calling second order? So, we will discuss more on this little later. The leading term which we are throwing starts at h square, that means h square will be the coefficient, okay, and the coefficient evaluated at x I t j, that will be multiplying h square. Similarly, here some other coefficient evaluating at x I t j will be multiplying k square. Okay. So, this is for the general case. Okay. So, we are proceeding along this. So, how long we proceed? Until we reach the boundary. Okay. Similarly, at different time levels. So, this time level corresponds to say t equals to 0, then this is t 1, t 2. Okay. Right. So, let us parabolic equations. So, the first one I am going to consider is heat conduction given by okay. So, where k is thermal conductivity, okay. K is thermal conductivity, which is supposed to be a constant. So, now we can go ahead with this, but typically from applied math point of view, when you solve such problems, this will be non-dimensionalized. Okay. So, we can do that. Even though this is not part of numerical solutions, I would like to just mention. So, that means see each k has dimensions. So, assume this is temperature, this is a time and then thermal conductivity. So, it would be better to non-dimensionalize, okay, so that the solutions are uniformly valid, okay, universally valid. Okay. So, how do we do it? We have to introduce new variables. X is space. So, we have divided by a length scale, okay, and u is temperature. So, by something, and these are called L and u naught, some characteristic quantities which are supposed to be known. Okay. So, if you introduce this, definitely with respect to x prime and u prime, these are non dimensional, right. So, okay. So, that is how we do it. Okay. So, if we proceed like this, we get remember I have not non dimensionalized T. So, in order this to be non dimensionalized, we go for this suggests the corresponding non dimensional time. Okay. So, when we go for this, so by dropping the primes, so you would have seen in many books with k, without k. So, that means you can arrive at such situation in with respect to non dimensional variables. Okay. Now, we are ready to discretize this. So, let me give the heading explicit method. So, I want to give the heading and proceed. So, consider the heat conduction equation. Okay. Say this is star. Then let us approximate star okay, by forward time and central space. Okay. So, forward time central space, by doing so u I j plus 1 forward time minus u I j equals, this is central space for the second derivative h square. So, if I do not mention anything, it is not nice. So, better we also mention this. What are these? For this approximation of the first derivative, this is the leading non-zero coefficient and correspondingly for the second order space. Okay. So, now these leads to J so I can take it k plus h square. Okay. So, we will talk about this definitely. Okay. So, I do not want to use the term right now, what is this? Okay. So, by doing so we get this. However, we further can simplify. Okay. So, u I j plus 1 equals to lambda u I minus 1 j, okay, plus 1 minus 2 lambda u I j plus lambda. Okay. Remember, I am not doing any trick, it is just algebra. Okay. Look carefully. Why did we pull j plus 1 to the left hand side? The reason is straightforward. So, the first order approximation we have used for the time, it is forward. Okay. So, which involves two time levels, that is j plus 1 and j, and the second order approximation for the space involves only one time level, that is j. So, now what is our aim? Given initial condition, we want to compute the solution by marching past, right, because this is an initial boundary value problem. Okay. So, in this case what we have to compute? We have to compute for all times the solution at various grid points. Okay. So, that means what are the time levels involved is an important issue. Okay. Because your discretized equation contains, let us say, 5 time levels, then we are lost completely. Okay. Because you unless you know at least 4 of them, you cannot compute. Okay. So, with respect to time level, we are trying to classify this method whether it is explicit or implicit. This is very much important. Okay. So, if you see this particular case, this entire discretized formula contains 2 time levels only. What are they? J plus 1 and j, which means essentially if you know the values at jth time level, you can compute at j plus 1 time level. So, hence we call this a 2 level method and explicit, okay, because of this nature. So, what is the remark? This is a 2 level method and this is explicit in nature because of this reason. Okay. So, 2 level means 2 time levels are involved. Okay. But in general in literature this may be because this is an important remark. So, when I say 2 level method means this involves 2 levels, otherwise strictly speaking the formula as it stands, say this is E. So, this E is in some sense one level time. Okay. So, because 2 level means the formula contains 2 levels only, but otherwise it is just one level, that means is required at one level to compute at the other level. So, that is it, in that sense you have to take it. Okay. So, now how this particular formula sits, let us see. Okay. So, this name of the method in literature used is Schmid method. Whatever formula we have obtained, so this is called Schmid method. Okay. So, it shows like this. Okay. So, you take any grid point, so this is x, this is t. Okay. Now, so you have to mark. So, this is say x I plus 1, x I minus 1, then say this is t j, then this is t j minus 1, this is t j plus 1. Okay. So, this is at I j, this is the point at I j, okay, and this is a point I j plus 1. Okay. So, if you recall the Schmid method, the formula is u I j plus 1 lambda times plus okay. So, this involves these points u I j plus 1. Okay. So, let me mark, and this is asking the function values at past time tap at which grid points, at I plus 1, I and I minus 1. So, u I j, then u I minus 1 j and u I plus 1 j. Okay. So, this is what is happening here. So, this one and this one. Okay. So, this is explicit, because if you know the values at jth time level, we can compute at j plus 1 time level. So, this is the explicit nature of this method. Okay. So, let us see with an example. Okay. Okay. So, u of x 0 is sin pi x, u of 0 t equal to 0. Now, see, this is a one time derivative and two space. Okay. So, u of, we need the boundary. So, this is two boundary conditions. Okay. Why? Because this is second order with respect to space. So, 1 t, this is also 0, and the problem domain is okay. So, now before we discretize, So, this is initial condition, this is boundary condition. Okay. So, let us discretize. So, this goes to u of x I 0, u of I 0, in the present case pi x I, and boundary condition u of, you should be careful. So, in this case what 0 corresponds to. So, remark x 0 is 0 and x n is 1, and what time step etcetera depends on our the specification. Okay. So, here x 0, okay, and this is for any t. So, therefore, t j is equals to 0 and this one x n for any t j equals to 0. Okay. So, this is the discretization. So, now it depends on the discretization, the step size corresponding to x and then t, the index will be decided. Okay. So, let us say h is given to be 1/3 and k is given to be 1/36, then lambda turned out to be, what is this? This is k by h square, the grid parameter. Okay. This is the grid parameter. So, accordingly x 0 is 0, x 1 is 1/3, x 2 is 2/3, x 3 is 1. So, since our domain is this, so this is x 0 and this is x n. Okay. Right. So, consider j equals to 0. So, then u I 0 is sin pi x 0, okay, x I, okay, sin pi x I u I 0. So, now you start I 1, start with I 0, okay. So, u 0 0 then I 1 here. So, this is I 0, I 1, I 2. So, I 1. So, that means we are computing the initial values at each grid point. Then I equal to 2, okay. Similarly, 3 0 this will be. So, now if you consider your discretized equation u, the discretized equation u I plus 1 u I j plus 1 is lambda u I minus 1 j I j, then put j equals to 0, okay, I equals to 1, because we want to compute the solution. The first value will be this, okay, lambda u 0 0, u 1 0, u 2 0. Okay. So, this can be computed. So, this will be so, similarly, at next grid point u 2 1. So, this is 1 by 4 u 1 0 u 2 0 u 3 0. So, this also you can compute. Okay. So, what is happening x 0, x 1, x 2, x 3. So, using j equals 0 values here, we have computed at j equals to 1 at each grid point. Okay. So, using the values at the first time level, we can compute that second time level, because it is explicit. Okay. Once we know the values at each grid point at a particular time level, you can march past and then compute at the higher time level. So, we will discuss more problems, so that we get a complete idea. Okay. Until then, goodbye. Thank you.